John.
All right, everyone, welcome back to the channel. Those of you, I believe, will remember the last edition we did of this with Matt LaCroix and John F. White. Now, back with us today, of course, Flat Earth Dave, Dr. Matthew Yelovich, and Angels of Light. We are going to be discussing some stuff that we didn't get to dig into last time. And, of course, we brought people from various fields to discuss this topic today. So what I want to do is get straight into it. Flat Earth Dave, if you could sum up in some shape or form, and I know that's a tough ask, the position that you've decided to kind of devote yourself to.
You know, I'm gonna switch it over to Angel because he just said it before we started recording. He's got the position now oiled down to basically 3 sentences. Go ahead.
All right. Well, yeah, our position is that we live on a level topographical plane. It's stationary. We're in an enclosed system. We have luminaries above us. We are geocentric, and all the luminaries rotate clockwise around Polaris, east to west.
Okay. So, Dave, nothing to add to that?
No, it's perfect.
All right. Matt, you've been on the channel before. I think so. Many people here will be familiar with you. Maybe you just want to throw us a very small introduction to the very least, and then kind of give us an idea of what you think about that model.
Well, it's good to be back, Will. Sure, I'll give a little introduction. I'm a professor of physics, fluid mechanics, and thermodynamics. I've been doing it for about 20 years now. So I have a pretty decent background in those areas. Hopefully it will be able to contribute somewhat to today's conversation. I'm a professional engineer. Prior to my work in academia, I worked in engineering for several decades. And here I am. So I just want to have a great discussion today. I want to hear the positions of both Dave and Angel, and maybe we could have a respectful discussion.
Awesome.
Starting right from there, obviously this model that Angel is presenting is a new one and will be a new one to a whole lot of people. And correct me if I'm wrong, and this is why you're here. Excuse me. This is why we wanted to have this discussion. These models and this model that he's presenting and the heliocentric model both cannot be correct. If I'm to understand this properly. Could you maybe help me make sense of why that is and how we can, how I'm supposed to make sense of a flat shaped model versus the one that we're obviously taught in school?
Yeah, you know, we have a model, if you will, but we realize that there's a lot that we don't understand. The globe doesn't have a model at all. The globe is the globe model, if you will, defies natural law. It has air uncontained next to a space vacuum. It has gravity, which is unproven, which defy electrostatics, which is proven, which is 10 to the 36 power stronger. We can go through all the different points and show you how, yeah, one of them is totally wrong, and one of them, we're certainly figuring it out. But we'll go over each one of those things and then let the listener come to their own conclusion. One thing I always say is don't believe anything that Angel and I say. Don't believe anything. Verify everything. We're gonna show you stuff that you never thought of. We're gonna show you stuff that you were programmed not to believe. And you know, belief is the enemy of knowing. For example, Matthew, test question: where do I live? We talked about it before the show. You can look down. You wrote it down.
Yeah, Connecticut.
Connecticut. Now, do you believe it or do you know it?
Well, I trust that you told me.
So you believe it?
Yes.
You believe it. So you heard me say it. You're like, why would he lie? He sounds like he's from Connecticut. He's got a little bit of a New York accent. That's near, you know, you stored that as truthful information, but you don't know it. You believe it. So we believe a lot of things that we've been told all of our life. But to know them, you know, I spoke to a principal and two science teachers the other day, and I said, what's your number one proof you live on a globe? And they're like, well, I never really thought about it. You know, they just believe it because that's what they were told. So I'll toss it back to either one of you guys. Where you want to go?
I guess we can start off with the first thing that Angel said, that we live on a, I believe you said level topographic plane. Is that correct?
Yep.
Okay, that's a good start. So let's define that. So are you saying that the Earth, as we know it, is not a sphere, correct? And that it is perfectly or relatively perfectly flat for all of its expanse. Is that correct?
Level and horizontal.
Yeah, level horizontal and has topography.
Okay, fair enough. So how long? Okay, if that's the case, let's just for the sake of argument say that that's the case, that it's level, flat, horizontal, whatever you want to call it. How far does it extend?
Okay, well that's the thing. Our known region, it would be Antarctica that we're allowed to go to independently. So past the 60th South parallel, there's actually an Antarctic treaty, and you have to get permission to be able to go further than the 60th parallel, which would be encircling the whole Earth.
Okay, I see the picture there. Okay, so you're saying that Antarctica is the outer border? Would that be the correct way to say it? The outer border of this known Earth?
Yes.
Okay.
Well, let me just chime in there. Antarctica is the shoreline that contains our water. Large bodies of water need containment. Now, does Antarctica, where we think Antarctica is, does it go all the way around, or does it go farther beyond it? We don't know because we don't have access. We can speculate, we can make claims, we can show evidence. But we don't know because we talked about the Antarctic Treaty. You have all of these islands out here. If everyone remembers the Falkland War for the little island, why are they fighting over that? These are where military bases run by the Crown are there, and they guard Antarctica. They don't allow anybody unsupervised, without prior permission to go beyond that 60 degrees south location. So there it is.
But people do go to Antarctica.
Absolutely.
Okay. So they've acquired permission to go there.
Yeah, but there's no free and independent exploration of the outer south.
Okay. All right. I am somewhat familiar with the Antarctic Treaty. It was signed by even the Soviet Union back, I believe, the Soviet Union and the United States, they all agreed on that treaty back in was it the 50s or the 60s?
Late 50s, right?
Okay. Okay, so let's go back to the whole flat plane. Now, the obvious arguments against that would be that the typical arguments we hear or even see is that as a boat moves out into the distance, you can see it the further out it goes past the horizon, which could be calculated. To calculate the distance of the horizon is probably not a big deal, but you could see that parts of the boat start to disappear, and then eventually the boat disappears over the horizon. Presumably, this would be going around the curve of the Earth, and that's why we can't see it. So that would be an obvious argument, a counter argument to the whole flat plane.
Sure. This is one of our.
Okay.
Let's. I mean, if you're done with that point, I don't want to go to another point.
It's just a good starting point. We can discuss that. I'd like to hear how you would argue that.
You agree you can't see my mouth right now, right?
No, I cannot.
Because it's behind a physical curve, a physical obstruction.
Yes.
So the globe has a required physical obstruction at a certain distance. And do you know what the curvature formula is by chance?
I could calculate it myself, but is the radius of the Earth? What is the radius of the Earth? I wrote it down.
3959.
30. What is that? Miles? I work in kilometers.
Yeah, miles.
Okay, I have 6,300. Okay, so what was that again in miles?
3959.
3959 radius. Okay. So you're asking me to calculate how much disappears over the horizon.
Right. So you don't need to calculate it now.
Okay.
We know it. We're going to tell it to you. Don't believe it. Verify it later so we don't waste it.
I have a calculator here. Go ahead.
So at 3 miles, the curvature is 6 feet. At 10 miles, it's 66 feet. Now, if we had a perfectly glass calm water day, cool, clear, no humidity, no pollution, so we have the best visibility, the farthest that horizon should be to a 6-foot observer is 3 miles away. Anything past that will start to get hidden behind a physical curve. Can you agree with that?
I think those numbers are correct. I just checked. There is an Earth curve calculator.
Yeah. So we have them. Verify them later, of course.
Yes, that sounds correct.
And if I sat down, I'm now no longer 6 feet tall. That horizon's going to come even closer to me because I'm lower.
Correct. Your perspective is different. Yeah.
So we're going to show you some observations that that require magical refraction. So out here, there's no boat. You can't see a boat. So look carefully. Ready? So as we zoom in, we're increasing the angular size. So we're making our aperture bigger and bigger and bigger. And as we do, all of a sudden you see, oh, look, there is a boat there. Now my finger can't hide that whole boat. But if my finger was a wave in the foreground, as I zoom out, my finger is going to hide the whole boat. Okay? And these little waves in the foreground, the boat looks like it's going over the curvature. But you can agree that boat's not going over curvature. It's going out of our ability to see it. It's going out of our angular resolution limits.
Yes, I agree. Yes.
If it was behind a physical curve, we couldn't zoom in on it. No, even if we had the Hubble telescope.
Well, there are other elements at play here, such as the refraction, but yes, I would agree that. How far is that boat away? Is that?
We don't know. We don't know on that one, but we do have other ones where, Angel, are you able to share images well, or I can share them and you can talk about them?
Yeah, I mean, I can share my own observation that I did. I've got the video ready. I can share it.
Yeah, some numbers would be good. If we could know how far away that particular object is, then we could calculate whether we can actually see it, then accounting for refraction.
Let Angel show you this demonstration, then I'll show you something that we know the exact numbers and you can verify.
Okay, great.
So just very quickly, right? You're saying that this horizon is curving down and away from us in all directions, correct?
Well, that's the model that we use in physics, correct?
Okay, so watch this. So it's going to reveal a buoy and a boat that wasn't previously visible, see? Now, my second question to you is, you just said that it's curving down and away from us in all directions. Now, my next question would have to be then, if that's the case, then how come when we zoom in onto the horizon, the boat in the distance appears higher in elevation than the buoy? If it's curving down and away, the opposite should be true. The boat should appear lower than the buoy. If you zoom all the way in on curvature that's curving down and away, it should curve more down and away from you as you zoom in.
No, do you know the distance of the boat there? I mean, the buoy.
I know my altitude above the water there was 6 feet.
All right, so you're at 6 feet, yeah. And how far away is the boat in miles?
We don't know the exact distance, but the point he's making here is the more distant object appears higher than the closer object. But when we're on a ball, we're always on the top of the ball, and the farther things get, the lower they should be. They go down and away. When you go across a ball, everything goes down and away.
Yes. I guess my question is, if we could have some numbers here, I know what's happening. I know what's happening here because the human eye can only see so far, and you were using obviously some form of camera. You were zooming in. Now it's easy to calculate how far that horizon line should be. You said you were at 6 feet. At 6 feet, the horizon should be about 3 miles away. So that horizon was 3 miles away from your perspective, from where you were standing. So that buoy was closer than that. That's why we can see it, right?
Correct. Yeah. No, well, we could see it. We could see it when I zoomed in. Yeah.
Yes, and again, human beings can only see so far. You know, if you were looking at a car or something, and you walk on a perfectly flat plane, and you walk further and further and further away from it, that car would eventually disappear. It would kind of merge into the horizon. It's perspective, right? So I guess the best way for the only way I can really analyze this is to know the distances, because if you show me something that I should not be able to see, then that would be a point well made. But right now, I don't know the distances.
I'm going to show you 2 points. Now, these are oil rigs, and we know exactly how far they are because they don't move, right? And the camera is 1 foot off the water here. Now, again, you need to verify this. I could be lying. It could be 100 feet in the air, right? So it's 1 foot off the water. This one is 6.2 miles away. Doesn't seem like far, 9.4 miles away. But according to the Earth Curve Calculator, this platform should be hidden by 59 feet of curvature from that elevation. Not only can we see all of the water leading up to it, we can see the horizon far behind it. We can see the horizon far behind it. Let me show you another video of this. So this horizon is far beyond the platforms.
Okay.
So right here, the water would need to be refracting up almost 60 feet. Out here, it has to refract up maybe hundreds of feet for us to be able to see it. But the horizon is far miles beyond the horizon, beyond the platform, which would be impossible on a ball.
Okay, so you're saying that the camera that took that picture was 1 foot off the water?
Correct.
So the first one was 1, this one's 8 foot, and I can actually show you the video of that confirming it, but yeah.
Oh, okay, so let's go with the 8 feet then. That's easy. These are easy calculations. So 8 feet, and you're saying that platform is 9.4 miles away?
The one in the back on that image now is 10.1 miles away from an 8 foot.
Okay, what's the one in the front? Because I can see that better.
About six.
Well, it doesn't matter because the horizon is far beyond the second one. The horizon, how can we see the water beyond it? The horizon should be in front of it.
Well, the horizon at that distance, at that height, so if you're 8 feet above, the horizon should be about 3.5 miles away.
Correct.
Yeah, there's an inconsistency there because the horizon, if that platform is, as you say, 6 miles away, then I can clearly see the horizon behind the rig. And that horizon in the background should be, like I said, 3.5, let's say 3.5 miles away, but it's obviously well beyond.
Something for you to look into. Something for you to look into and confirm.
Now, again, these are pictures that you're showing me, but let's just, for the sake of argument and, to have a good discussion, let's just assume all the numbers are correct. Then that is inconsistent with the Earth curve calculation. But however, we have to factor in refraction, but refraction is only about, at most, it could only reduce curvature probably by about 7 to 10% at most. So it wouldn't.
Could I get in here about refraction?
Yep.
Now, the law of refraction is Snell's law, which actually requires 2 different isotropic mediums. Now, number one, if you're going to invoke a density gradient, crepuscular rays go through the density gradient and they do not curve. Now, second of all, when we're looking horizontally over the Earth, there's no density gradient. Okay, because we're looking horizontally. The density gradient is vertical. So you can't really even invoke refraction on the Earth, to be honest.
Unless the Earth is curved.
When you say density gradient...
No, you can't. You're right, because it would be the same density. You're right.
When you say density gradient, you mean the change of density of the air from the surface all the way up.
Yep.
Yeah, if we calculate how much refraction there would be from the top of Mount Everest to sea level, it's 0.0%. It's negligible.
No, refraction. You're right that refraction is not a big factor. Like I said, at most, it would probably be in the range of a few percent, maybe 7%. It wouldn't account for that much of it wouldn't cause that much more to be visible over the curve of the Earth. So I don't think refraction is a huge player. It is a minor player. We can argue, how much, but based on that rig that you showed me, something doesn't seem right there. Assuming the numbers are correct, I'm taking your word for it.
Club Libertas, the elite private membership club for the modern mystic, exploring powerful teachings on spirituality, self-awareness, ancient wisdom, a deep dive into meditation, mindfulness, and transformational practices designed for those ready to lead their own journey. Are you ready to step up?
Matthew, let me just a side note here. I'm going to share a playlist with you after the show or whenever, and listeners, you can post it. It's a list of experiments that were already done where we show we document everything. That way you can watch those and then reproduce any ones you want. But we've done all the work for you because these experiments, You got to go out there. The conditions have to be right. If it's wavy, there's an issue. If there's, fog, right? So all of these have been done. We have dozens and dozens and dozens of videos for you to watch. But here's another one that we had a guy do on a lake. So large bodies of water at rest lie flat. When they get cold, they freeze flat. So here is a canal or a lake. We got a camera 6 inches off the ice. And in the video, you can see that he dug down, shows you where the ice is. So we're not on top of any snow or anything. And then he put these lights at 8 miles, 7 miles, 6 miles, and 5 miles. Now, that doesn't seem far. But at 6 miles away, the horizon should be 0.88 miles away, less than a mile away. That's the Earth curve calculator, and we're looking on ice.
Sorry, at 8 miles, is that right on the surface of the water?
It's right on the ice.
Oh, I see.
And I think these are 6 inches off the ice, right? But again, you have to watch the video. But again, 6 inches a foot isn't going to make a difference. Watch. At 8 miles, including an absurd amount of refraction, 30 feet, 22 feet, 15, and 9 feet behind the curve of the Earth. Remember? Mm-hmm. You can't see my mouth because it's behind the curve of the Earth.
Yes.
Okay? So if we look at it, we have two options. We got the camera on the ice, and it's looking at all of these things across the level ice. That's option number one. Option number two is the camera 6 inches off the ice at 0.88 miles away is the tangent of the Earth. It's skimming across the tangent, and all of these at nighttime with no humidity are refracting up and stopping exactly at that tangent line. None of them are going above. None of them are going below. They're just magically stopping at that tangent line. Option A, flat Earth. Option B, heliocentric religion.
Yeah, the only way to be able to see those multicolored lights would be to invoke refraction.
Or flat Earth.
Well, yes. I mean, again, there's two options here. So there's the absolute flat Earth, and that way you should be able to see them, assuming there's no density, obscuring, the further you see. That's why we can't see Mount Everest from, eventually.
That's not why. Oh, no, you can't because of the density. You're right.
Correct,
You're absolutely
correct.
right.
So assuming the density is not an issue, it's a very low humidity day, then the only way to see those lights are either, according to your theory, the Earth is perfectly flat, or there's some form of refraction that is bending around the Earth. But again,
you got to take point, right, that this is on a frozen lake, so the refraction levels will be at a minuscule.
No, and I agree with that. They would be relatively minuscule at that temperature, and it's frozen, so I assume it's sub-zero degrees centigrade. Now, you said that the water is perfectly flat, but it wouldn't be perfectly flat because the water on a globe would, follow the shape of the globe. So the water of that lake would actually be, curved according to the globe, right? It would freeze curved. Does that make sense?
Exactly. Yeah.
Yeah.
But we're seeing the lights, though. They're not blocked by curvature.
Yeah, again, there's no the only explanation, assuming everything you're showing me is correct, and I have no reason to think otherwise, then it would seem that would be, as they say in Star Trek, an anomaly.
Yeah. You mentioned Everest.
One sec, Dave, because I know obviously the listeners here are going to be able to get, and I know with our limited time.
Can we go over an hour? I hope we can go over an hour.
100% we can go over an hour.
Okay.
Yeah, don't worry there.
Okay.
But given that we do have what we're doing, I want to make sure that I think to this aspect, I think they have at least some understanding of the position here within this, and I want to make sure we hit some of the points that are also going to be on their minds, and precisely space. And we discussed this a bit, but there are obviously going to be some huge issues with satellites, stars, gravity, etc. And so I think
those are good topics for this discussion.
Yeah, I think we should hit that right there.
I want to just do one more curvature point, then we can change topics. Is that cool?
Okay. All right. Perfect. Go ahead.
Angel, you want to say something, or you want me to go? I'm going to talk about Canada.
Oh, I was ready to go for the gas pressure, but go ahead.
All right. Well, that's space. We'll go to space next. So
okay.
Here's a spot from Alouge, France, and it's a famous spot because twice a year you can see Mount Canada, but Mount Canada is 175 miles away. And at 175 miles from this altitude, which I don't know off the top of my head, but we can look it up, the top of Mount Canigou should be over a half a mile below. Are you paying attention, Matthew?
Yeah, I'm listening and calculating as you speak.
The top of Mount Canigou, well, you don't know the elevation height, so you can't calculate.
Okay.
100, and the top of Mount Canigou should be a half a mile. And almost every day of the year, you can't see it. Earth curve, right? But twice a year, the sun lines up with the viewer in its migration between the tropics. And when it goes beyond Mount Canigou, you can see it. And right there, the top of Mount Canigou and the whole mountain is seen. The top should be over a half a mile below the curve. Let me just jump forward a little bit.
There
So the globe explanation here is, that mountain is over the curve, right? And the sun is also has also set. So the sun has also set, but it's refracting up, and Mount Canigou is also refracting up and blocking the refracted sun.
Well, why don't you try infrared photography? That way you could, you should be able, with infrared, if Mount Canigou is actually visible, then you don't have to wait twice a year. You could use infrared and you should be able to see it anytime, I think.
That actually is a great idea.
We have done it, but just I want to make another point on this. Now, would you agree refraction is the bending of light?
Mm-hmm.
Just simply?
Yeah,
okay.
That's a simple definition, yeah.
What we're seeing here, though, is a silhouette of the mountain. Now, the silhouette would mean the absence of light. Now, you can't refract the absence of light, but we're seeing the mountain, which means would have direct line of sight to it.
Right. And here's an infrared shot from Malibu to Mount San Jacinto, whatever. I never get it right. I'm going to give up trying. 123 miles. That's almost 7,000 feet of curvature. This mountain is barely over 7,000 feet, so we should just see the top. But when we take off the infrared lens, blue sky, little smog, blue sky.
Yeah, infrared will allow you to see it because, again, if you're just looking at it through a regular camera. So you're saying that's 123 miles away?
Yep. Earth curve will not let you see it.
No, not at 123 miles. What is the observer height there?
I don't know off the top of my head, but it's not high. And they're from whatever 7,000 feet of curvature comes to, that's the height.
That's about three kilometers at that distance. How tall is that mountain?
Just over 7,000 feet.
Yeah, you shouldn't be able to see that.
Welcome to Flat Earth.
But again, I mean, refraction could not.
Infrared cuts down refraction also. Infrared makes less refraction.
Again, I'm going with these things you're showing me, so I
And as I said, don't believe anything we say.
Understood.
Don't believe anything we say. We're just pointing out these things. And the playlist I'm going to give you, we document it all so you can see that it's all legit. And then you can go out and repeat them yourself if you like.
Well, there are experiments. I mean, there's actually some very simple experiments to prove whether the Earth is a globe or a plane. I'll give you an example. So if you have two buildings that are, say, I don't know, 50 kilometers apart. So when they build those buildings, plumb bombs, the buildings are always built perfectly vertical. So on a globe, the buildings should look like this, right?
Yeah.
Right? So at 50
I know where you're going with this. I know where you got this from too. And it's been done. The World Trade Towers were built right next to each other, right? Yeah. And on a globe, the top should be farther apart than the bottoms, but they weren't. But you can't measure accurately 50 miles.
Sure you can. Sure you can.
How?
There's you could use okay, when you use lasers and stuff like that, that might introduce issues such as refraction and things like that. But you could use those super highly accurate civil engineering GPSs. What you do, you go 50 kilometers apart to two nearly identical buildings. And if the Earth was a globe, they should do this. So you put one of those super tracker GPSs on the base of each of the buildings. You measure the distance. They're accurate within like 2 or 3 centimeters. They're crazy accurate. And then you take the same GPS and you put it on the top of the buildings. Now, there should be a difference at 50 miles, probably from the top and the bottom of both buildings, maybe a meter or two, and that should be easily measurable. So that would be an experiment that should should be pretty easy to do. You just need to get your hands on those. I think they're called. I don't have a. Yeah, they're super high precision. They use them in civil engineering. They're good within a couple of centimeters. So that way, if the tops of the buildings and the bottom of the building have the same distance, then the Earth is flat. If there is a difference between the top and the bottom, then the Earth is a globe.
What do you say, Angel?
Well, you got to remember though, we've done observations like I can share it if you want. I'll just put it on screen just to show.
But just one other thing is how tall is this building? Because at 50 miles, could the buildings even see each other? And if we do see them, doesn't that prove that the Earth is not curved?
Well, according to your theory, you should be able to see them. But again, then we introduce things like refraction and things like that. But if you take the optics out of it and you use GPS, then you're not really invoking any refraction or light issues or laser measurements or anything like that. You could actually get a pretty accurate fix on them.
Well, Matthew, on screen, can you see my screen that I'm sharing?
Yes, I do.
Okay, so this is Chicago skyline across Lake Michigan. This is 57 miles in distance away from the observer. Now, this was taken at Grandmere State Park across to Lake Michigan. They're both elevated. If you calculate so the observer height is 600 feet above sea level, and Chicago skyline, the base, is 577 feet above sea level. So you minus that to get the actual height above sea level, which is 23 feet. And then you add 6 foot for the camera height and you get 29 feet. Now, at this distance, there should be over 1,600 feet of curvature. Now, that top building there, the tallest one, Willis Tower, that's only 1,450 feet high. So the top of that building, tallest one that you're seeing there, should also be below the curve on this observation.
What is the observer height here?
When you do the calculation above sea level, it's 29 feet.
That's not a sea. Isn't that a lake?
What's the calculation above? How high are they above the lake?
Yes, that's what I need to know.
Because sea level doesn't matter, and a lot of Globers don't realize that.
Yeah.
Do you know, Angel? Is it 8 feet or something? Or
well, his observation height was 600 feet above sea level, but the other side of the lake is also elevated 577 feet above sea level. So that's why you'd have to minus it to get the height above sea level.
All right, let's assume he's 8 feet above the lake.
No, he's 29 feet, I think, right?
Oh, okay, that's fair enough.
29 feet, yeah.
So the hidden height should be 1,700 feet.
Yeah, roughly.
Yeah, no, exactly.
What's the tallest building in Chicago, Angel?
1,450 to that top there. There's an antenna that you can't see, but it's too small to see at that resolution. But yeah,
if you look at mine, you can see it right here. Here, switch over to my screen, and I'm going to put on. This is a time lapse. Now, refraction would happen under atmospheric conditions. Atmospheric conditions change throughout the day. So here's a time lapse. I'm going to keep my finger right on this building right here. Yep. And we're going. I think this is like almost 18 to 20 hour time lapse. The building isn't moving. It isn't wobbling. It isn't miraging. It isn't changing. It isn't doing anything. It's staying exactly where it is. And we're going to go into the night, and nothing has changed. We can see it all. There you go.
Wow, that must have been a super clear day.
It certainly was.
Now, that's impossible because of the distance at 52 miles.
Unless the Earth is flat.
Well, okay, I'm not ready to go there yet. But
okay, all right. Here's what I want you to say, though. If you find something that's impossible on a ball, just clarify. You can say that's impossible on a globe. All right?
Okay, at 50, if these pictures are correct and those distances are correct, at 52 miles, even accounting for refraction, even if it was a 7 to 10% refraction, none of that. Was that Chicago, you said?
Yeah.
Chicago skyline, yeah.
Yeah, none of that Chicago skyline should be visible based on...
Matthew, just very quickly, that exact photo was on American news, and they were telling people that was a mirage that was refracting above.
A mirage would have to be upside down.
Welcome.
Thank you.
How could that mirage? Who said that? Who said that was a mirage?
It was, what was his name? Cooney. I can't remember his... Yeah,
was it like a newscaster or a
Yeah.
Yeah.
Oh, well, then we can discount that.
He was a meteorologist, I think he said, actually.
A meteor, like a weatherman?
I believe so, yes.
Yeah, I don't know about the mirage thing.
So here, let me show you this.
What's
Whoops,
that?
hold on, wrong thing. Hold on 1 second. Let me get rid of that. So this happens a lot, and the science magazines and newspapers everywhere, they're like, floating ship, it's a mirage, and they're explaining how this ship is floating in the air, and they're giving all this Fata Morgana mirage, and it's so clear, and people are freaking out. Right. Well, so you can make up all of this stuff for the globe. Or you could actually just look at it a little more careful and understand that this is water that has wind on it, and this is water that doesn't. The sky is very nondescript. So if I crank up the contrast, I draw in where the real horizon is, I'll throw a little city there, then you could see that it's just sitting on less water that doesn't have a wind line on it.
I've actually seen this in reality, and yeah, that is not mirage at all. You just can't see the water where the actual ship is.
You can't see the water because it's reflecting. So this is another one. This was in just last year. A bunch of magazines had a floating ship up in the sky.
Well, these are just optical illusions. We can
if we crank it up, you can see the water around the ship. It's just reflecting the vanilla sky. So again,
okay.
They love using mirages, but mirages kill them all the time.
Well, I don't know. I can't comment. I mean, that Chicago skyline thing doesn't look like a mirage, but...
All right, let's shift to space.
TheWayOfWillJohn.com. Exclusive content and programs on manifestation, making money, hidden knowledge. Finally, reach your full potential.
Yes, let's shift a little bit before we get to space, and I think this has already been beneficial for plenty of people that are just getting introduced to the subject. There is one thing just before we get into space, which we discussed last time, Dave, which was the movement, the speed of the Earth. What I'd like to get Matthew's understanding on. And so if you could just explain the speeds with which we were moving, and I think it's interesting just because I don't think most people know what it is that we believe to be our speeds.
The Earth is rotating at 1,000 miles an hour. No one's gone 1,000 miles an hour. You've gone 500 in an airplane. It's orbiting around the sun at 66,600 miles an hour on average. Funny number. It's chasing the sun. The sun is moving through the sky. And we're going around it, chasing it at over 500,000 miles per hour. And somehow all of the other planets stay on the same plane around, and they're all chasing the sun and its curved trajectory around the galaxy at 500,000 miles per hour. And then the entire system's moving sideways at something like 2.2 million miles an hour. That's probably a wrong number because all the numbers are wrong because we're not moving, right? So you have to believe in this crazy thing with gas balls in a space vacuum, flying in all these different directions, gravity holding everything in perfect order, never, ignoring the three-body problem, and somehow everything just works perfectly. Angel, you want to chime in?
Yeah, I just want to ask you real quick, Matthew. Turning is acceleration, right? Would you agree?
What do you mean turning?
Okay, so when you're turning, say in a plane, when the plane's turning, it's changing vectors constantly. Therefore, it's accelerating. Okay, now you would feel that motion, correct? Now,
yes,
we don't feel the Earth. We don't feel the Earth accelerating or moving, and they claim it actually does change speeds.
If all of those velocities, okay, I mean, those numbers that you threw out, they actually sound right. I think I remember those numbers seem about right. So what we have here is it's an inertial reference frame. So there's no change in velocity. Like let's just assume, I mean, there's centripetal acceleration but let's just assume that there's no changes in velocity. So if the Earth is moving at, what did you say, 66,600 miles per hour or something like that?
66,000.
It's at a constant velocity. So it's in an inertial reference frame. So no.
So really quick, the actual orbit is actually said to go from 29 kilometers a second orbit to 30. Now, if you do that in miles per hour, that's a change of 2,200 miles per hour.
You mean it's changing its velocity?
Yeah, supposedly as it goes around the sun, it's going faster and it slows down and faster and it slows down. That's what we're taught.
We actually see the sun speeding up in the south and covering a longer distance in the south because of that. But they claim the Earth is doing it.
Okay, let's backtrack here. So if we're in a non-accelerating reference frame, so like say you're on a big yellow school bus and you're traveling 100 kilometers per hour on the highway, you can walk around, or an airplane. Let's use an airplane. If you're in an airplane traveling at a consistent velocity, 500 miles per hour or whatever, you can get up, you can go to the bathroom, you could drink wine and things. You don't really feel that you're moving, but once the plane either accelerates in the positive or accelerates in the negative direction, then the acceleration, it becomes a non-inertial reference frame, right? So
let me address that.
Yeah.
You want to go? Do you want to go, Angel?
I'll go real quick. So you're assuming that the plane is going in a straight line, though. Now, if the airplane is turning,
it would be
that's acceleration. If the plane turns, that's acceleration.
correct. Yes.
So hang on. So
you would feel it.
We're in that school bus. We're on a perfectly smooth road, great suspension, going 100 miles an hour, no problem. You can drink your tea. You can go to the bathroom if they had a bathroom on a school bus. But if we got a plate of water, a dinner plate, filled it with water,
yeah,
and that bus took the slightest turn or changed its speed the slightest amount, the water is going to go right off the plate.
correct.
Right. So we're dropping the curve of the Earth. If you're on the equator, dropping at a mile per minute to follow the curve of the Earth. If I was going 1,000 miles an hour in an airplane, I have to drop at a mile per minute just not to go into outer space, right? If I'm in America, right, and the Earth is spinning, not only am I going, let's call it 500 miles per hour because I'm halfway to the North Pole, we'll say, but I'm also turning because the spin of the Earth should throw me out towards the equator. Right? East and west are circles on a flat Earth and on a globe Earth. They don't prove either, but they're not straight lines. And if we're spinning, I'm turning all the way around. So when I'm facing west, I should be leaning to the south because that turn should be pushing me to the south. If I had a plate of water, there should be more water on the south side of that plate because I'm turning at a mile per minute.
Hold on a second. There's some kinematics involved here. When a plane takes off, it is not taking off at zero velocity. Like it will be taking off at the initial velocity of, say, the Earth spin. So there's initial velocity relative to there's a velocity relative to the Earth, and then there's a velocity if you look from outside the Earth down. Now, when you said the plane, when it's flying, it would be did you say curving down or nosing down?
It would have to nose down.
On a globe, would have to, yes. And it doesn't do that in reality.
Yes, to maintain altitude. And they are traveling at relatively high speeds, 600 miles per hour.
Yeah, right in there.
The navigation system of the plane would have to follow the curvature of the Earth.
Yes.
Otherwise it would continue straight out into, space, right?
Can I show? I've got my my flight simulator. If you want to see it, I can show you that real quick.
Yeah, sure. It's interesting stuff.
Okay, so in reality, I've debated many pilots. They all admit they don't need to nose down in reality. Actually, I debated a pilot the other day. He was really interested and, was pretty much getting flat smack left, right, center. He had to rethink his whole world. But yeah, this is a globe. This is the actual dimensions of the globe. And if I start the flight, it's going to take off, and it's got the attitude indicator here, which maintains rigidity in space. Now, as the plane flies, I'm just going to speed it up a bit. You're going to notice that because it's curving down and away from the plane's just going to keep gaining altitude on the top.
The Earth is curving down and away.
Yeah, the Earth is curving down and away from the plane. Now, if I just leave it in straight and level flight, this is how the plane flies in reality. It doesn't nose down. But because it's not nosing down on a tangent, it's going to end up in space eventually. It's going to be just gaining altitude into infinity.
Well, I don't think it has to have enough thrust and energy to get up there. I don't know if a plane, but then again, gravity is getting weaker the higher it goes, so it would require less thrust.
No, so gravity would have to pull only the nose of the plane down, though. It had to be selective in this case. Also,
but don't the airplane navigate, like most pilots do not fly by stick over the course of their flight path. If they're flying from Miami to Rome, they're not actually flying across the Atlantic by stick. They're using the autopilot system. Wouldn't the autopilot system simply correct for the altitude, meaning that, yeah, every minute the Earth is falling away, but wouldn't the autopilot system just simply correct the altitude to keep the plane at the exact same altitude that it needs to be? That makes sense.
It does, but over a flat Earth, because what happens is this attitude indicator has a gyroscope in it, which maintains rigidity in space. And if the plane was following
a gyroscope, yeah.
If the plane was actually following a curve, as you can see now that I'm nosing down, it's changing. It's showing a nose down in the attitude indicator on the left there. Because, and as you fly, if I've debated a pilot, right, who flew 4,800 miles with the nose up, and we've got pitch data to support this. The plane doesn't nose down in reality. It just maintains a...
Well, you can feel it. When you're on a plane, it almost feels like you're always flying with the nose a little bit tilted forward. You never really feel that it's nosing down. But I guess the question is, what about those, okay, for those large commercial airliners, they're all teched out now. They have so much, they have, autopilot systems and all that. But what about a small, regular, non-technological plane like a Cessna or something like that? The pilot would...
That makes it worse.
The pilot would have to correct for the Earth falling away.